Hello everyone. This presentation provides a summary of a PhD thesis research project entitled Influence of LC3 on the Service Life of Reinforced Concrete. The research was conducted by Alejandro Fernández Domínguez, a professor at the Technological University of Havana, under the supervision of Professor Fernando Martirena from CIDENT at UCLV in Villa Clara, Cuba. This presentation begins with an introduction to the research problem and the specific goals that guide the study. Next, the materials and key methods applied in the experimental research are presented. Then the main results are shown and discussed, and finally, the conclusions derived from this investigation are shared. The service life of concrete structures was defined by Tutti in 1982 as the sum of two distinct stages. First, the initiation period, when aggressive agents such as chlorides penetrate through the pore matrix. Second, the propagation period, which begins once these agents have reached a threshold value and continues the deterioration progress. Both stages are fundamentally linked to one critical factor, the density of the pore matrix. The use of supplementary cementitious materials has become one of the most effective strategies for enhancing durability. These materials greatly reduce the number, size, and interconnection of pores in the concrete matrix. In this context, limestone calcined clay cement, commercially known as LC3, has been extensively studied over the past 2 decades. Research has already demonstrated that LC3, made with only 50% clinker and with a calcium clay to limestone ratio of 2:1, even using low-grade kaolinitic clay, can produce concrete with mechanical strength at 28 days, comparable to conventional concrete. This is achieved while obtaining a 40% reduction in CO2 emissions and the use of raw materials that are abundant worldwide. In terms of durability, at lab scale, LC3 concrete has already proven a high resistance to chloride ingress, an increased chloride chemical binding, and an enhanced resistivity. These results reflect how LC3 refines the pore matrix through a synergistic reaction between its three main components. Besides the pozzolanic reaction between calcium clay and portlandite, which produces additional cash, two other reactions occur, one between the calcium clay and the limestone, and another one between the portlandite and the limestone. These two reactions produces mono and hemi carboaluminates, which further densify the microstructure. While laboratory tests had already clearly demonstrated LC3 potential, the next crucial step was to evaluate its influence on the surface life of reinforced concrete structure under real exposure conditions, and we made that our research goal. To achieve this goal, in 2014, an exposure site was established in Punta Matamoros, Cayo Santa Maria, located on the northern coast of Villa Clara in the central part of Cuba. Reinforced concrete blocks with similar mixed design were precast using both OPC and LC3, and then placed at the exposure site in late 2014. Between 2015 and 2018, annual core extractions were performed and various durability tests were conducted. The study was paused due to the COVID-19 and subsequent economic challenges in Cuba, but it was restarted in 2024, this time focusing especially on rebar corrosion after a decade of exposure. Let's dive into some of the results, and starting with carbonation. The graph shows carbonation depth versus the square root of time for both mixes. As can be observed, the values for OPC are almost double to those for LC3, clearly demonstrating how the finer pore structure limits CO2 penetration. However, as expected, the carbonation rate is higher for LC3. This is attributed to its lower buffering capacity, resulting from the high clinker replacement rate and the significant consumption of Portland dye in the synergistic reactions previously presented. When projected to 50 years, the predicted carbonation depth remains insignificant for the durability of these reinforced concrete elements. Now let's check the total chloride profiles. Total chloride concentration as a percentage of concrete weight was measured during the first 3 years of exposure at depths of 10, 20, and 30 millimeters. As expected, the LC3 samples consistently show lower chloride concentrations than OPC at all depths and exposure periods. It should also be noted that the differences in chloride content between the two concretes increases over time. This observation will be addressed in the next slides. The air permeability using the Tolman method was other test applied on the cores extracted from the elements. On the graph are shown the KT values versus the year of exposure. The KT values for LC3 were consistently 1 order of magnitude lower than those for OPC at every measurement, again demonstrating the finer pore structure of LC3 systems. After the third year, a sharp increase in KT values was observed for both mixes. This is related to the surface wear of the concrete elements, caused by the ethylene guide leaching, which becomes soluble in the presence of chlorides, by seawater erosion, and also by salt crystallization. It can be noticed that LC3 elements exhibited much better resistance to this surface wear than OPC elements. This is because the finer pore matrix of LC3 concrete limits seawater penetration, thereby reducing surface damage. This phenomenon also helps explaining the chloride results presented in the previous slide. Since chloride diffusion is governed by surface concentration, the superior surface wear resistance of LC3 contributes to the growing difference in chloride content over time. Regarding electrical resistivity measured using the Venner method, values for LC3 concrete were consistently between 2 to 4 times higher than OPC elements. These findings align perfectly with the trends observed in other durability tests and with the published literature. In terms of time evolution, OPC concrete shows a slight increase in resistivity, likely due to the ongoing reactions in this highly humid environment. For LC3 concrete, a steady increase over time is observed, indicating that the synergistic reactions are still ongoing, at least after 3 years of exposure. These results are consistent with findings by Zunino and Scrivener from 2022. Electrical resistivity is not only an indicator during the initiation period, It is also a key parameter that defines the deterioration rate during the propagation period. The kinetics of electrochemical corrosion reactions are highly dependent on the electrical resistivity of the concrete, and this will be demonstrated in the following slides. Corrosion propagation was first examined through visual inspection of the rebars after extraction of the 2024 cores. These images taken with an optical microscope reveal a remarkable contrast between the two concrete systems. While the rebar from OPC concrete shows extensive corrosion products and an almost 3 mm pit, the LC3 concrete rebar shows only corrosion products that appear to be superficial, with no evidence of deep pitting. To quantify the visual observation, corrosion rate was measured through weight loss analysis following HTM-G1 using chloride acid. After carefully cleaning the rebars to remove corrosion products without damaging the base metal, the mass loss for each sample was calculated. The results were striking. Rebars from OPC concrete had lost significantly more mass than those from LC3 concrete. When the actual corrosion rates were calculated, the difference became even clearer. Rebars inside LC3 concrete corroded at a rate approximately 4 times lower than those in OPC after 10 years of marine coastal exposure. Corrosion propagation was further analyzed after cleaning the rebars. Images also taken with an optical microscope show the true extent of the damage. As can be observed on the rebar from OPC concrete, the pitting is denser and pits are deeper and wider, indicating advanced localized corrosion that affect large areas of the surface, giving the impression of a general corrosion. In the case of the rebar from LC3 concrete, the pits are smaller and more spread out. The damage is less concentrated, with large areas of the surface still intact, and no deep or wide pits are visible. All this evidence strongly suggests that LC3 provides superior protection to embed reinforcement, limiting corrosion to the surface level even after 10 years of marine exposure. These observations are consistent with recent findings on the high electrical resistivity of LC3 system, which restricts corrosion currents. The key conclusions derived from this decade-long study are the following. LC3 has proven to have a significant impact on enhancing concrete resistance to chloride ingress under real marine exposure conditions, confirming what laboratory studies had suggested. Rebars inside LC3 concrete corroded at a rate 4 times lower than those in OPC concrete after 10 years of marine coastal exposure. These findings demonstrate that LC3 is not just an environmentally friendly alternative. These findings demonstrate that LC3 is not just an environmentally friendly alternative, it is a durability-enhancing alternative that can significantly extend the service life of reinforced concrete structures in aggressive marine environments. Thank you all for your attention. For those interested in learning more about LC3 or collaborating on future studies, you can find the author contacts herein.